All right, last lesson we looked a lot at how to simplify radicals, how to use power properties. I encourage you, if you don't have all those rules for radicals and rules for exponents memorized, please revisit that section often to help you out on those. But now we're going to be moving on to intercepts and looking at what those tell us. So the x-intercepts of the graph of the function f of x are very important because they're solutions to the equation f of x equals 0. That's the same as setting y equal to 0. In past tasks, we learned how to find the x-intercept of the function by factoring, which works great for some functions, but not for others. In this task, we're going to work on a process to find the x-intercepts of any quadratic function that has them. And we'll start by thinking about what we already know about a few specific quadratic functions, and then use what we know to generalize to all quadratic functions with x-intercepts. So we will go ahead and look at that. Let's start in on number 1. Well, what can you say about the graph of the function f of x equals x squared minus 2x minus 3? Well, the first thing that we can say in this standard form is we know that the y-intercept will be negative 3, because if we set x equal to 0 and then solve for f of x, we would get f of x is equal to negative 3, because we just plug in zeros for x, right? But that doesn't really tell us how to graph the function all that well. So instead, what we should probably do is put this thing into vertex form and then graph. So remember that our vertex form, we've got this formula for a times x plus b over 2a quantity squared plus c minus b squared all over 2a. Okay, so that's how we can put this into vertex form. Let's go ahead and do it. Remember, our coefficients are the numbers directly to the left of our variables, right? So a in this case is just 1, b is negative 2, and c is negative 3. So we can just go ahead and plug all those values in. If a is 1, we don't actually need to include that right here, because multiplying or dividing anything by 1 will keep that thing as itself. So I can just omit that and say x plus b over 2 times 1 again is just going to be 1. And then, oh, I should actually put in the b. The b is negative 2. So negative 2 over 2 quantity squared, and then it's plus c, which is negative 3, minus b squared. Notice I put that b in parentheses because I need to square the negative as well, all over 2 times 1, which is just 2. And now I can go ahead and simplify. So in here I have x minus 1, because negative 2 divided by 2 is just a negative 1. Outside I've got plus a negative 3, which is just minus 3. And then I have this negative 2 squared, which is positive 4, divided by 2 is 2, but a negative sign out front. So I've got minus 2 again there at the end. So my entire vertex form will be x minus 1 quantity squared minus 5. Okay, so my vertex should be at 1 comma negative 5. Oh, I just found something. Let me make a quick correction. This should be over 4a, not over 2a. That is my fault. So it's 4 over 4, which then would make this right here actually 4 divided by 4, which is just 1. And that would make this negative 4. So glad we caught that here, but that's my bad. This should be in the formula over 4a. Now I have the vertex of this function, which is just at 1 comma negative 4. So I can go ahead and plot that on this coordinate plane right here. So here are my axes. Notice I've got them a little off center. But there's my vertex right there at 1 comma negative 4. And then as in graphing any parabola, I just go over 1 up 1. It doesn't have a stretch, so it's over 1 up 1, over 2 up 4. Oh, and look at that. It gives us our x-intercepts as well. And then I connect those with a smooth curve. All right. So the equation now of the line of symmetry, remember the line of symmetry is the line across which this thing would mirror itself. So that's going to be right there. I also know this to be the x value of my vertex. So the equation of the line of symmetry is a vertical line at x equals positive 1. Okay, and the vertex of the function finally is 1 comma negative 4. So I can see this correlation right there. So let's think specifically about the x-intercept of f of x equals x squared minus 2x minus 3. I'm also just realizing we could have factored that pretty easily. But in any case, we went ahead and did vertex form, so that's what it was. But what are the x-intercepts? Well, we could see them right here at -1 and +3. So I've got x equals -1 and x equals +3. And now the question is, how far are the x-intercepts from the axis of symmetry? So if I count these spaces right here, I see that each of those x-intercepts are 2 away from the the axis of symmetry. So they are 2 units, let's say 2 units away from the line of symmetry. So if you knew the line of symmetry was now instead of having a numerical value, it has this value of h, and you know how far the x-intercepts are from the line of symmetry, how could you find the x-intercepts? Well, you should be able to take h, which is this dotted line right here, theoretically, right, h, and add whatever the distance away is, and subtract, right? So it should be h plus 2 and h minus 2. Wow. H minus 2. Okay, so that's just an interesting thing to note. Now it also asks us how far above the vertex are the x-intercepts, and if we just count the vertical shift, we're not counting diagonal or horizontal shift at all, but if we just count the vertical shift, we could see that the x-intercepts are 4 above the vertex. Okay, just counting up there gives us 4. Now, finally, also, what is the value of f of x at the x-intercepts? Well, what's the value of the actual function? The value of the function is 0, right? Because it's going through the x-axis. So f of x equals 0 as it passes through that x-axis. So just to make it a little bit easier to talk about some of the features that relate to the x-intercepts, let's name them with a variable. So from now on, when we talk about the distance from the line of symmetry to either of the x-intercepts, we'll call it d. Notice that above, d was the same, right? On the positive side, it's 2, and on the negative side, it's 2. Okay, so d is going to be the same on either side of the axis of symmetry, okay? Now, we call that d, and the diagram below shows that feature. We'll always refer to the line of symmetry as x equals h, so the two x-intercepts will be at the points h plus d and h minus d. Okay, so if h is the axis of symmetry, then the intercepts are h plus d, and h over here would be minus d, okay? Because it is d distance, all right? So let's think about another function. What we're going to do is this one, we actually need to put it into vertex form. We cannot factor that function. So we're going to go ahead, and it's a good thing we got practice with it just a second ago, but we'll go ahead and put this one into vertex form as well, using our handy dandy little formula over here over 4a, not over 2a, my bad. But again, we see that our a value is 1. Now our b value is -6, and our c value is 4. So let's go ahead and plug those in. I've got x plus -6 over 2 times 1, which is just 2, quantity squared, plus 4, which is my c, or plus c, which is 4, minus -6 squared. Notice I put the entire b in parentheses so I can square the whole thing all over to 4. I almost did it again. 4 times 1, which is 4. So let's go ahead and simplify this. This is x minus 3, because -6 divided by 2 is -3, plus 4. -6 squared is positive 36 over 4, and 36 over 4 is just 9. So when I simplify this, it's going to be 4 minus 9, so that's a -5. So I get the vertex at x minus 3, quantity squared, minus 5. Okay, so I need to graph that now using that vertex form, where the vertex is at 3, -5. So I'll put some axes out here, and then go over to 3, comma -5, which is right down there. Okay, and then I can go ahead and go over 1, up 1 squared, which is 1. Both directions. Go over 2, up 2 squared, which is 4, because there's no stretch. Over 3, up 3 squared, which is 9. Right here and right there. Okay. Now I can connect all of these points with a smooth curve. Okay, that curve was not very smooth. There, that's a little better. Let's try that one. And over on the left-hand side, wow, bad start. There we go. That one's a little smoother. Okay, there we go. And let's answer the following questions. What's the vertex? Well, we found it right here. Remember, we changed the sign when we bring it out of parentheses. Keep the sign when we're not in parentheses. So the vertex is 3, -5. What's the equation of the line of symmetry? Well, that's always just going to be the x value of our vertex. So x is equal to 3. And what do you estimate the x-intercepts of the function to be? Now, we can all get our own estimations, but here's the axis of symmetry, right? And I see this as probably being, here are the x-intercepts. That one's like 0.8, maybe 0.9. This one's probably at about, let's see, 3, 4, 5, 5.1 or 2, maybe. Let's go 0.8 and 5.2. I think that's about close. You can, if your graphs look a little bit different, you're welcome to make different estimations, but you just need to account for that. So 0.8 and 5.2 are what I'm estimating. So then the question is, what do I estimate D to be? Remember, D is the distance from the axis of symmetry to the x-intercept. So what I should have is these should be the same distance away from 3. So if I go 5.2 minus 3, that should be 2.2. And if I do 3 minus 0.8, that should be 2.2, and they both actually are. So the important thing to note is that if you're estimating x-intercepts, they just should be they should be the same distance away from the line of symmetry, x equals 8. X equals h. So then this question here again, what is the value of f of x at the intercepts? Well, the value of the function should always be 0 because that's where it's actually crossing the x-axis, right? Now in G, it says using the vertex form of this equation and the answer to part f above, write an equation and solve to find the exact values of the x-intercepts. So up here, what I omitted and what I often will omit is just the f of x equals, and this function right here is f of x equals. That's function notation, right? We could sometimes get sucked into this idea of just like writing this portion, but I do need to remember that this is actually a function, right? So if f says f of x is equal to 0, and I also have that f of x is equal to x minus 3's quantity squared minus 5, then I need to be able to use both of those statements to set up an equation and solve for x. So if f of x equals 0, I can plug in 0, I could plug in 0 for all of f of x. So I can go 0 is equal to x minus 3 quantity squared minus 5. Okay, and then I can solve for x. That's what I'm actually going to do to find the exact x-intercepts. So I add 5 to both sides, and I get 5 is equal to x minus 3 quantity squared. Take the square root of both sides. Remember that plus or minus, right? And on the right side, pew pew. So I get the plus or minus square root of 5 equals x minus 3. Note this cannot be simplified any further. If I could simplify it, I should, but I can't right now. So I'm just going to go ahead and leave that as the square root of 5. Add 3 to both sides. So I get the exact value of the x-intercepts of x equals 3 plus or minus the square root of 5. Okay. So the next question now is, what is the exact value of D? Well, remember that our x-intercepts are technically like h plus D, right? Where h is the axis of symmetry, which in this case is 3. So h plus D will be 3 plus D in this case. So when we look down here at our solution of what our x-intercepts are actually equal to, we see that it's h, or 3, plus or minus the square root of 5. So the exact value is the square root of 5. Now, some of you might say, well, can I put that into my calculator and see what it gives me? You could, but that would be an inexact value because we would have to round it. 5 is an irrational number, which means it goes on forever. So we can't put that into our calculators and get an exact value. So the exact value, the only exact value, is the square root of 5. Now, though, we can use a calculator to find approximations for the square root, or for the x-intercepts, and see how they compare to our estimates. So we've got x equals 3 plus the square root of 5, and x equals 3 minus the square root of 5. And then we plug that into our calculators and we get rounded decimals. So let's go ahead and do that. 3 plus the square root of 5. For that one, I get 5.23, hot dog, or 5.24 rather. And then 3 minus the square root of 5, that is 0.76. Okay, so my estimations were 5.2 and 0.8, which are pretty close. Like if we rounded those, I would be all right. But they're not very exact, right? Also, these decimals continued on. I just rounded them. Those decimals actually will continue on forever. So we can't write down that entire decimal. So this is exact, this is inexact, or approximations, right? Okay. So we got pretty close with our estimates, but they were not exactly on point, right? But we also figured out how we can use the vertex form to find the exact value of those x-intercepts. So now let's talk about a function with a vertical stretch. Could we find the exact values for the x-intercepts in the same way? Well, let's try by first graphing the function by putting it into vertex form. Now, our a is equal to 2, b is equal to -8, and c is equal to 5. So now I can't just say, oh, the a goes away because 1 multiplied by anything is just itself. So this is a little different, right? So now I have to do 2. And I'll use that formula again, plus b squared, which is -8, quantity squared, all over 2a, which is 2, quantity squared, plus c, which is 5, minus b squared. Oh, actually, this one in here is not squared. My fault. Sorry. -8 squared. Remember, I put that entire thing into the parentheses, so I square the entire -8, all over 4 times 2. Okay, now I can simplify and see what it gives me. So I've got 2 out front still, times x, and then -8 divided by 4 is just -2. So it's x minus 2, quantity squared, plus 5, and then -8 squared is 64, all divided by 8. Well, that is, so -8 squared is positive 64, right? Divided by 8 on the bottom is just 8. So the vertex of this equation is going to be, or the vertex form, simplified, is going to be 2 times x minus 2 quantity squared minus 3. All right? So the vertex, I'll just answer this real quick. Vertex is going to be at 2 comma -3, because remember when I put something into, or take something out of parentheses in an equation, I need to change the sign. I'll say that f of x is equal to this just to kind of remind us of that function. And I'll plot that vertex. So the vertex is at 2, -3. So here we go right here. Vertex is at 2, -3. And now when I plot it, I need to account for this stretch that's happening in this function. Okay, so now it's not going to be over 1 up 1 squared, which is 1. It'll be over 1 up 1 squared times 2. So 1 squared is 1 times 2 is 2, right, in both directions. I would normally go over 2 up 2 squared, which is 4, but now I'm going to go up 2 squared times 2, which is 4 times 8. So I'll go 2, 4, 6, 8. Here's my next point. And connect those dots with a smooth curve just like this. Oh boy. All right. So a pretty steep parabola. But it asks us next, what's the equation of the line of symmetry? Well, they've said x equals h, but we also know that it's in numerical value, x equals 2. It's the x value of, or the x portion of our vertex, right? Now, what do we estimate the intercepts to be? Boy, I would say they're actually going to be pretty darn close to 1 and 3. So I'm going to actually say 0.9, maybe 0.9 and 3.1. Now, remember also, when I'm estimating d now, d is this distance right here, and that is, I have estimated it to be 1.1, because 2 plus 1.1 is 3.1, and 2 minus 1.1 is 0.9. Okay, so I've estimated d to be approximately 1.1. And what's the value of f of x at the intercepts? Well, f of x is equal to 0 because that's where the function is at 0. Y move, it's touching the x-axis. Okay, using the vertex form of the equation and the answer to f, where f of x is equal to 0, write an equation and solve it. So if f of x is normally equal to 2 times x minus 2 quantity squared minus 3, just like up here, now I'm going to plug in 0 for f of x because that's what I've said right there for those x-intercepts. So 0 is equal to 2 times x minus 3 quantity squared minus 3. I did that incorrectly. It's x minus 2 quantity squared. There we go. That's right. So this is the process by which I can find x-intercepts. Okay. So I'll go ahead and add 3 to both sides. Add 3 to both sides. I get 3 equals 2 times x minus 2 quantity squared. Now before I can do the square root, this is where I have been just doing a square root, but I'm actually going to go ahead and divide both sides by 2 first. So I have that square by itself on the right, and then I can have an easier time of taking a square root. Boo-boo. Square root of both sides. Remember, when I square root the other side, I have to insert the plus or minus. So I've got plus or minus the square root of 3/2 equals x minus 2. Doggone it, I did it again. It's x minus 2 over there. Sorry, guys. And finally, add 2 to both sides, and I get 2 plus or minus the square root of 3/2 is equal to x. Okay. So that is the exact value of my x-intercept. So now what's the exact value of d? Well, remember, it's what I've added and subtracted to the axis of symmetry, which in this case, the axis of symmetry is x equals 2, right? So you can see that showing up right here. So the exact value of d is the square root of 3/2. Okay. Now let's go ahead and say, okay, what are those values and compare it to our estimation? So x equals 2 plus the square root of 3/2 and x equals 2 minus the square root of 3/2. Let's see if it's close to our 0.1 and 0.9 and 3.1. So I plug that into my calculator. Let's see. And I get 3.1, or 3 divided by 2. Take the square root of that. That's actually 1.2. So it's going to be closer to 3.22. And and 0.78. Okay, so D is actually, if I were to estimate D, that would actually be closer to 1.22. And this is my actual, these are the actual roots, right? Where actually I shouldn't include an equal sign, I should include an approximately sign, because those are estimations, right? Or not estimations, but they are rounded decimals. Okay. We were close, still not super close. It's better to be exact and find the real deal there. Okay, number 5. Finally, let's generalize this process by using f of x equals ax squared plus bx plus c to represent the quadratic function that has x-intercepts. Here's the possible graph. So we've actually been using this vertex form in this function already. Or in this form already. We've been saying it's f of x equals a x minus or plus b over 2a quantity squared plus c minus b squared over 4a. So we've been using that for a little while, right? So the vertex of this parabola, it's kind of a shortcut for us. The vertex of this parabola, though, then, is negative b over 2a comma c minus b squared over 4a, right? Because we have this in parentheses, so we change the sign. And then everything out here, we can't simplify that any further, so we're just going to bring it right out there, okay? So there's the vertex, and now we have to say, okay, what's the line of symmetry? Well, the line of symmetry is just the x value of the vertex, so it's going to be negative b over 2a. And we need to write and solve the equation for the x-intercepts just like we did previously. So this now is where we're going to put 0 in, or plug 0 in for f of x, and solve for x. So this one's going to be kind of tricky, but we've got 0 equals a times x plus b over 2a quantity squared plus c minus b squared over 4a. Okay, and we need to try to get x by itself. So what I see first is I want to get rid of additions and subtractions. So I'm going to add b squared over 4a to both sides, and I'm going to subtract c from both sides. So minus c plus b squared over 4a. And the next line should read negative c plus b squared over 4a is equal to a times x plus b over 2a quantity squared. Okay, so right here I also see this little like fraction here, whole number here. Let's make those both fractions so that we can have, we're about to divide out this a over here, and it's easier to divide an a if we have one fraction. So the way that I'll do that is multiply this negative c by a well-chosen 1, right? So I'm not changing its value because 4a over 4a is just 1. I'm just making it into a fraction that I can add with b squared over 4a. So what that becomes is negative 4ac all over 4a plus this b squared over 4a. So when I write that all down, I'm going to do two things here. So remembering this is 4ac over 4a. I'm going to do two things. I'm going to change the order of these two as well because I don't like having this negative sign out front by itself. So I'm going to do this next line will be b squared minus 4ac all over 4a. So that's this portion. I'm just writing it second now. And that is all equal to a times x, plus b over 2a. Okay, quantity squared. Now I can divide out both sides by a. When I'm dividing out by a on the left-hand side, all I have is just an a times a in the denominator now. So I get b squared minus 4ac all over 4a squared equals x plus b over 2a quantity squared. Okay, the next step now is square rooting both sides. Boo-boo. Square rooting both sides. Now remember, when I square root the fraction, I can square root the numerator and square root the denominator separately. And I want to do that because I see 4 and a squared both have are perfect squares, right? So the top cannot simplify because even though b squared is a perfect square, there's a subtraction right here. This only works when there's just multiplication between the two, so I can't separate out these two terms under the top square root. So it's just going to be b squared minus 4ac, the square root of all that, all over the square root of 4, which is 2, and the square root of a squared, which is a. And I get that equal to x plus b over 2a. Oh, I forgot something. Plus or minus when I take the square root. So I've got plus or minus, right? Now finally I can subtract b over 2a from both sides. Oh, and look at that. This is actually common denominators already. So I can just put this negative b in the numerator, and I will get negative b plus or minus the square root of b squared minus 4ac all over 2a. Well, does that look familiar or what? This is all equal to x. I hope that looks familiar because this is actually the quadratic formula. So what we just did is we actually, using the general term of the vertex form, we were able to actually solve for the quadratic formula right there. That's pretty incredible. Okay, now let's use that to kind of use it as a shortcut and say, okay, what are the solutions for the x-intercepts of this function right here, where we've got a is equal to 1, b is equal to negative 3, and c is equal to negative 1. So let's go ahead and use that equation. I've got minus negative 3 plus or minus the square root of negative 3. I'm going to square that whole thing. minus 4 times 1 times negative 1 all over 2a, which is just 2. Okay, and now I can simplify. Minus a negative, whoop, becomes a positive. So I've got 3 plus or minus the square root of negative 3 squared is positive 9. Minus 4 times positive 1 is negative 4 times negative 1 is positive 4. So it's 9 plus 4 all over 2. So to simplify this one more step, I get 3 plus or minus the square root of 13 all over 2. And I cannot simplify that anymore. This radical is as simple as it gets because 13 is a prime number. All right. So number 7, you may have found the algebra for writing the general quadratic function f of x equals ax squared plus bx plus c in vertex form a bit difficult. But here's another way we could work with the general quadratic form that leads us to arrive at the same thing we should have arrived at in 5D. Since the two x-intercepts are d units from the line of symmetry h equals x, the quadratic formula crosses the x-axis at its x-intercepts that are h minus d and h plus d. Now we could always write that in factored form, where the x-intercepts, or the factored form, would look like this. Now they have replaced negative p and negative q to be saying these x-intercepts. So they're actually saying that those are equal to these two terms right here. Okay, so what we're going to try to do now is rewrite this factored form right down here in terms of the x-intercepts using h minus d and h plus d. So remember that if we have those x-intercepts, we are going to actually change their sign. So we'll say a is times x, and we change the sign of this thing in here. So it's minus h plus d. That's one factor. And then we change the sign of the thing over here, minus h minus d. X minus h minus d. Just like that, okay? Now we're going to have to multiply this trinomial factored form, which is very similar to foiling or loifing, but instead we have to multiply every term in the first trinomial by every term in the second trinomial. So what that kind of looks like is this right here, where you distribute the x through, and then you'll distribute this negative h through, and then you distribute this d through. Okay, so there's a lot of things happening there, but we'll do it kind of systematically, leaving that a out front until we simplify everything inside this multiplication. Then we can multiply the a through if we need to. So x times x is x squared. X times negative h is negative xh. X times negative d is negative xd. Then, done with this first one. So now I can go to that negative h of the first term. So negative h times x is negative hx. Negative h times negative h is positive h squared. Negative h times negative d is positive dh. Okay, just like that. Then I have, let's see, I'm done with that second term, so now I'm on to the third term. So I've got plus d times x minus d times h and minus d squared. And now I'll try to simplify this as much as I can in like terms. Now, remember, if I have two numbers like 3 times 4, that's equal to 12. Is 4 times 3 also equal to 12? Yes. So if I have 3 times 4, I can also write that as 4 times 3. Okay, so whether you have xd or dx, those are like terms, right? Because it doesn't matter the direction that you're multiplying, they're going to be like terms. So what I can look at is I can actually find like terms in here. X squared is by itself. It doesn't have any other x squareds. Let's see, xh, I have two xh's. So I'm done with that one, but I've got negative h minus xh, so that's negative 2xh. Done with those ones. And then I've got negative xd and a positive dx, where negative xd plus dx is just 0. So those just cancel each other off. Then I have this plus h squared here. And then I have a plus dh and a minus dh. Those two cancel off because anything minus itself is just 0. And then I have a negative d squared. Okay, so I've got that whole big thing right there. And now I want to think about that if I can in any other way. So I actually am going to multiply this a through now because I want it to look a little bit more like the ax squared plus bx plus c. So I'm going to multiply that through and say a x squared minus 2axh plus a h squared minus a d squared. Okay. And finally, what I'm going to do is I'm actually going to put this in terms of that typical ax squared plus bx plus c. Maybe a little bit easier. It might be a tiny bit easier to look at if I think about this in terms of the ax squared, this in terms of the bx, and this in terms of the c. Now, another way I could write this is ax squared minus 2ahx, so that I can see this a little bit more clearly as like, oh, this is my b term right here. And plus, and then just for fun, I'm going to say h squared minus d squared with this a factored out. I can, since they both terms have that a, I can factor it out. Okay, so now I have the different form where it looks like standard form, right? Ax squared plus bx plus c, but a is the same, b is different, and c is different, right? So now let's see. It says that is b, the coefficient of x is in of one version of the standard form is equivalent to this thing right here in our new form that we just found. It's equivalent to negative 2ah, okay? Likewise, c, the constant right here, is equivalent to a h squared minus d squared. Okay? So then what we need to do is solve the equations b equals negative 2ah and c equals a h squared minus d squared for h and d. So they want us to solve this in terms of b and c now so that we can solve for h and d. Because remember, our h is representing axis of symmetry, which I will sometimes abbreviate like this, and d is representing distance from axis of symmetry. Okay, this one is the simplest, so let's go ahead and start with that. B is equal to negative 2ah, and actually to get h by itself, all I have to do is divide both sides by negative 2a. So I get h is equal to, that is b, I get h is equal to negative b over 2a. Just it's more proper to have the negative sign in the numerator. And then if this is h, when I'm dealing with this second term right here, I can actually plug that in for h so that I only have one variable that I'm working with. I only have the d that I'm trying to solve for. So I get c is equal to a times negative b over 2a squared minus d squared. Okay. To solve this kind of thing, I will do divide both sides by, divide both sides by a, cancels off over here, and I get c over a is equal to negative b over 2a all squared minus d squared. Okay. And now I'm going to I'll go ahead and put this square through where I've got negative b squared, 2 squared, and a squared. So I get c over a is equal to b squared over 4a, okay, minus d squared. So I need to get d squared by itself so that I can simplify it further. So I'll subtract b squared over 4a from both sides. Nope, 4a. Okay, and I get negative, I get c over a minus b squared over 4a is equal to negative d squared. This, I should get like terms over here, so I'm going to multiply by 4 and 4. Oh, and this is a squared. My bad. So I'm going to multiply by 4 over a. 4a over 4a, rather. So I get 4ac all over 4a minus b squared all over 4a. Oh, shoot, and these are both a squareds. Equals negative d squared. Now, because these have the same denominator now, because I just made common denominators, I can plug that all in up here and put them all over just 4a squared. Okay, now I have a negative that I need to divide out, so divide by a negative, divide by a negative. That's going to distribute through to be negative 4ac all over, or negative 4ac plus b squared. When I do that, I'll write the b squared first so that I don't have to have that negative out front. And that's all equal to d squared. Take the square root of both sides and I get plus or minus here. Boop, boop, those cancel off. Remember that this is the same thing as putting the square root in the numerator and the square root in the denominator. The reason that's important is because d is now equal to plus or minus the square root of b squared minus 4ac all over the square root of 4, which is 2, and the square root of a squared, which is a. Wow, that's really interesting. I look at this and I look at this, and those look like pieces of the quadratic formula, right? H plus d is my x-intercepts, and if I were to add those two together, I would have negative b plus or minus the square root of b squared minus 4ac all over 2a, right? Which is actually the next question. H plus d are the x-intercepts, or h plus or minus d rather. So then I've got negative b over 2a, and the plus or minus is already built in over here on this d. Square root of b squared minus 4ac all over 2a. They're all over the same denominator, so I can say x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, just like that. Now, how does our answer in E compare to 5D? Well, it's actually identical. It's the same answer as in 5D. Okay? The same. So all the functions that we've worked with on this task have had graphs that open upward, but do you think the formula would work for parabolas that open downward? Tell us why or why not. So they should work with a being a negative number. It should still work just fine. Because of this a outside of the radical right here, it will kind of fix itself so that if it opens downward, we'll still be able to get the x-intercepts. So there you have it. Good luck on 3.5.